Okay, let's look at some examples of equilibrium problems. Don't forget, an equilibrium problem means that the net force is actually equal 0, and it also means that the object is not changing its motion. That might mean it's standing still, or it might mean it's moving at a constant velocity. In this case, the object, the gymnast to the right, is standing still. So we could say that the net force acting on her is equal to 0, which is equal to 2 times the forces in the cables minus the weight acting down. If we wanted to take this and solve for the tension in one cable, we could rearrange this and say 2 times F is equal to the weight, and of course the tension is her mass times gravity divided by 2. So 65 kilograms times 9.8 newtons per kilogram over 2. Let's see if I can get some help here from the calculator. So you just move me. 65 times 9.8 equals divided by 2 equals. That is about 321 newtons. Okay, so let's see what we have. Okay, well, they got 318, I got 321. I'd say that's pretty close. Let me see, what was the difference? No difference. Well, I think I trust my calculator better. So, solving equilibrium problems. I hope everybody's enjoying the bird in the background. Solving equilibrium problems. Here are the problem-solving steps. Draw the free body diagram of the object. Name all the forces. Set the net force, that is, the sum of the forces, equal to 0, taking into account plus and minus for the directions, and solve for the unknown force. Okay, and this is what we had for the gymnast, right? 2 forces acting up and her weight acting down was equal to a net force of 0 because, well, you could see right away she wasn't accelerating, so her net force acting on her was actually 0. So let's see. 2 masses are at rest, connected by a rope that passes over 2 frictionless pulleys. The string tension T equals M2G. Which of these free body diagrams best represents the forces acting on mass M1? Well, let's see. So the thing we're isolating is M1. So let's just see. We have a surface here pushing up. Right, that's Fn acting upward. We have a tension in the string, which is, of course, really the weight of M2, so M2G, which is going to pull up on this. So we have 2 forces acting in the upward direction, and the weight is M1G. So if I were to say that the net force is equal to 0, I would also have to say that it would be the normal force plus M2G minus M1G. Which of these free body diagrams best represents the forces acting on mass 1? Well, I would say it was A, because B is okay, but it's missing the normal force. I don't know where that is. And C is a little strange because the tension is pushing the object down, according to this. You can't really push something with a string. It doesn't work too well. So that leaves us with choice A as the correct free body diagram. Okay, I hope everybody sees that. Okay, so our suspicions are confirmed. Two masses are at rest, connected by a rope that passes over frictionless pulleys. The string tension T equals M2G. Which of these free body diagrams best represents the forces acting on mass M1? Diagram A is best. Well, it's actually correct too. Diagram B omits the normal force from the floor, and diagram C incorrectly shows the string tension acting downward. Strings don't act in compression. Okay. And a 10 kilogram dumbbell resting on a table is partly supported by a spring that pulls upward with a force of 50 newtons. Draw the free body diagram for the dumbbell. Well, let's see if we can do that. So we have two normal forces. One here, one over here. We have the force of the spring acting up, and we have the force of the weight acting down. Okay, that looks like a pretty good free body diagram to me. And there it is. What is the magnitude of the net force acting on the dumbbell? Well, if I were to just add all this stuff up, it's F plus 2Fn minus mg. If this is 10 kilograms times 9.8 meters per second, it's, well, I'll just say minus mg, but it's going to be minus 98 newtons. So if this thing is at rest, right, that means 0 is equal to 50 newtons up plus 2Fn minus 98, which means 98 newtons down. Okay. Through the mysteries of algebra, I'm going to say that 2 times the normal force is equal to 48 newtons. And if I divide through by 2, I get normal force is equal to 24 newtons. So there are two normal forces of 24 newtons each. Okay, well, that was the assumption. We couldn't know because we didn't know the normal force. We know it's 0 because simply because it says it was at rest. Figuring out what the missing normal force was optional, but of course we did, and we know that each one is 24 newtons. Okay. What force does a table exert on the dumbbells to hold it up? Well, we just found that. It's a total of 48 newtons, or 24 newtons for each side of the dumbbell. Okay, here's the total, 48, and that's for 2 times the normal force. And if we were to divide that by 2, we would get a normal force equals 24 newtons. Okay? I hope that takes care of things. I hope everybody has a really good understanding now. Do the problems that follow the video. Okay, see you guys soon.